Hello, my name is Diana Ceballos, and I will be presenting on the introduction to exposure assessment. So I'm going to share my screen. And I would like to acknowledge the Socio-Environmental Research Group to invite us to give this talk. The learning objectives is to understand exposure concepts and the role of exposure assessment in environmental health, discuss how environmental exposures can affect health, and describe different methods and approaches to measure exposures. And lastly, explain key aspects on the analysis of exposure data. So what is exposure assessment and what is an exposure? How does an exposure get into the body? How to measure an exposure? And basics on how to analyze exposure data, having in consideration that more and more in public health, it's important to conceptually consider the joint contributions of toxicants and social factors. And we'll end with some conclusions. So what is exposure assessment? It's a collection and analysis of quantitative and qualitative information needed to understand the nature of contact between receptor and a stressor, with a receptor being a people, a person, humans, and ecosystems, and the stressors being, for example, particles in air and lead in dust, or other stressors. And more broadly, exposure science captures the spatial and temporal dimensions of exposure events with respect to acute and long-term effects on human populations and ecosystems. And so what is an exposure? We have a lot of things that are external to us, and then things that are inside our body. And so an exposure is the contact between that stressor and receptor over an exposure period. And so an exposure is something external to us. When dose is the amount of that stressor that enters the receptor after crossing an exposure boundary and is already inside the body. And so exposure assessment looks at everything outside of the body and the absorbed dose in the body, all the way from sources and emissions to where these contaminants are, both media, for example, air or water, versus microenvironments. Is it the home or the workplace? And then it results in an exposure. And this measurement of all of these and understanding all of these is exposure assessment. So now typical stress agents include chemical, physical, and biological agents. Chemical could be, for example, solvents. Physical can be extreme heat or climate change. Biological, the COVID pandemic. And some exposures may cause adverse health effects. So for example, lead from leaded gasoline, BPA in plastic bottles, extreme heat, COVID-19, living close to a highway. And there's going to be also exposures that have a positive health effect. And so, green and trees, blue spaces like bodies of water, nutrition, physical activity. But then how does an exposure get into the body? So there's different variables that conceptually frame core elements in exposure science related to humans and ecosystems. So first we have a source of an exposure, but depending on who we are and our unique characteristics, as well as how often are we in contact with this source and our typical time, activity, and behavior patterns, will determine how much exposed we are and how much it actually goes in our bodies. And then depending on how much we are exposed to them and how much it gets to the body, then the outcomes and the health effects will follow. So now thinking about how things get into our body, we need to understand first routes of exposure. So we would have inhalation, if things are in the air, ingestion, right? If things are in food or in dust, absorption, if things are liquid or go in our skin and the chemical or the contaminant is absorbed, or the eyes. And then we have injection. Say, for example, we work as a nurse and we were injected with a contaminated syringe. And then once we have that clear, say, for example, our analyte of interest is heavily inhaled, so we want to measure the air. What are the next steps? How to go about measuring an exposure? Well, first, we have to have a very clear research question, because depending on our research question is that we are going to get a good answer. And then we should be ready to answer all WH questions: what, when, why, and how, because by going question by question, we're going to be understanding exactly what to do. And so one example is, say, you really want to measure solvents, but you don't know which solvents. So one possibility that you could do is you can check the methods that you may have available to you to measure solvents. And some methods are going to give you more solvents than others. Some methods may give you a sum of all the solvents. And so making the decisions of what you want to choose is part of the process. So now, the next step is to understand if we have the ability to measure exposure directly. So for example, doing personal monitoring of a person, doing a badge that measures the solvents in the breathing zone, or we want to do biological markers. Say, for example, we want to draw blood, take a blood sample of the solvents, or we really can't do that, and we may need to do something more indirect, but maybe enough. We may be asking them how often are they in contact with solvents, and they do self-report questionnaire, and that's okay. We can do some modelings based on some observations that we gather of the situation. We can even do some area sampling, make some assumptions about exposure, collect some diaries. There's many different ways to go about it. But say, for example, you set out to measure your exposure because you have some instruments and you know what you want to measure, then there's definitely considerations to do. So for example, you want to understand if you want to do personal sampling, like this nail salon worker with some personal samplers on her, or we want to do area samples because we actually, maybe there may be only one worker in that nail salon, but there's different things happening and we want to measure how much variability there is inside the shop. It could be that we have both real-time and continuous measures, and so we want to choose which one is better for what. And then having very clear understanding of the timing of the exposure versus the sampling. And so, say, for example, we know that with this particular sensor, we can only measure grab samples, like 1 minute at a time, or it only measures continuously. And then we also want to understand the exposure side. And so we can do a lot of observations to determine if the exposures are constant or not. And then, you may have many different people that you're sampling, but you may already know which ones are the exposed population, and you want to define that very well. And then at the end, you may have many different options for doing a monitoring, but you want to really be careful in what to do if you have so many options, because there are advantages and disadvantages. And so, for example, if you choose a standard method, then it's going to be much more comparable. You may have previous research that gives you some comparison, and it may be well established in the field, and novel techniques can be very inexpensive, fun and new, and maybe easy to use, but may not be as validated, and it brings some challenges for what you may be doing. But acknowledging what you're going to be using is the first step. So now, just a note in terms of biomarkers of exposure, depending on the analyte, you may want to choose the best biomarker that reflects, if possible, the dose in the body, because those are the best biomarkers. However, not all biomarkers express dose. And so if you're not able to collect that, you can collect other biomarkers, but at least acknowledging that. There's many advantages and disadvantages on using biomarkers, but one of the main disadvantages, besides being expensive and labor intensive, is that timing is very critical. And so, for example, if you're collecting lead in blood, it's not so critical, the timing. But if you collect benzene in blood, because benzene is very volatile, the timing with the exposure is very critical. And so having that in consideration is very important before making decisions on when to sample. Other analytical considerations are that instruments and laboratories may give you information that needs to be converted before it has units that relates to an exposure. And so, say, for example, you send these samples to the lab and you may get only mass of benzene per sample. Then you may need to understand what is the volume of air that you collected so that you can calculate the concentration of benzene with that information. It could be that an instrument only gives you a number of particles in a sample, and you need to calculate the number of particles per minute to be able to create a unit that is more related to exposure and easier to compare. And you can look at the literature for these. So now, another critical thing that has come from experience in working with folks that are not always related and as familiar with exposure science is that it's very important to look at limit of detections in your samples. And before considering any further data analysis. And so understanding the percentage of samples that are above limit of detection is critical. And if you have a high number of samples that are not detected, then you may need to be thinking very carefully on how to analyze that data, because it becomes a little more complicated as it doesn't abide by the traditional descriptive statistics and other statistics. So now, to do a data analysis plan, it's very important to define your exposure variables. Think of validation of the methods and in the field, any checkpoints and confirmations that the data is in good shape. Doing some quality control. Say, for example, you run the instrument in background versus expose, so that you can see that the baseline is actually well below and that the instrument is doing well. Sometimes the instruments can be calibrated. You can do cal checks. You can do a lot of blanks. And there's many other ways to do quality control. And lastly, for data analysis, remember that with exposures data, you may find nonlinear and non-parametric associations very commonly, because not everything is normalized. And then mixed methods are very important, because you will likely be using qualitative and quantitative data. And so the reason is because in nature, most exposures are found in log normal distributions. And so they're not going to behave in a normal curve. It's going to likely have a tail, like the figure to the right. And this means that the logarithms of the measured values are the ones that are going to be normally distributed. And so when you have log normal data, it's very important to use central tendencies that actually describe that distribution. So geometric mean or a median are highly encouraged instead of a mean. And then some of the strategies for data analysis is to compare exposure groups because this gives you great discussion or interpretation of your data. And so you can contrast exposed versus not exposed, contrast different populations or different conditions. And so in my nail salon research, for example, I have compared for example, salons that do not use acrylic versus salon that use acrylic. So that would be exposed versus not exposed. I have compared the nail salon workers with the general population. So that would be comparing different populations. And I have compared before the shift and after the shift for solvents. And that would be contrasting different conditions. So now another tool that is very important to put in context your exposure data is comparing to established health guidelines. And so government, at least in the United States, and there may be other international guidelines, like OSHA, CDC, EPA, and HUD have very good guidelines to compare with. However, to compare exposure data to guidelines, you have to be very cautious that you're using the same or similar media and the same units. And this means that you cannot compare an air concentration with a soil concentration just because they have ppm, because it's different types of ppm. And now I would urge everyone to only use occupational guidelines if you understand them very well and use them with caution because they're truly designed for workers. And so they're not always as relevant. So now to end, I would like to walk you through some of my research and an example of how I approach this conceptual framework of exposure assessment for the understanding of lead exposures in homes of lead exposed construction workers. And so if we look at the external sources, we have lead in paint, in water, garden, or on dust from work items. And then as media, we would have dust, dirt, or water. As a microenvironment, we would have the home, so inside, the garden outside of the home, and then we also have the car, because especially if the worker uses the car and the family uses the same car, then there's potentials for lead exposed workers there in their families. And so now in terms of exposure for homes, in particular, the literature suggests that ingestion is the primary route of exposure. And then if we're actually going to be looking at what exposure variables I collect from the dust, I usually do a vacuum sample, surface wipes, observations, age of the home, worker survey. For dirt, I usually take a sample or do observations outside of the home. And then for water, I'm not collecting actual samples because I don't have the capability or the resources to do sample of the water analysis. But I often do observations and ask the families to provide me if they've had reports of lead in water in the past. So now finally, looking at the internal side of the exposure assessment, I also take blood samples to determine lead in blood. And so that way, we can relate these with lead poisoning and then many of the other health effects related to lead poisoning in children. So now in my study of contaminants brought to the home from the workplace, it has been very evident that lead is not the only culprit because the realities of these workers is that the likelihood of a worker having a house that is poorly maintained, has lead paint, is very high compared to many other demographics. And then on top of that, they also bring lead from work. And so there's definitely overlapping vulnerabilities in these populations. And so as an exposure scientist, I have to acknowledge social factors into my exposure assessment. Thus, in my studies, I usually try to gather the most information possible in terms of the individual worker factors, socio-demographics, a little bit about their workplace, about their occupation and industry, more about their home and neighborhood, and then individual family factors that are playing a role in all of these dynamics to make lead poisoning in children coming from workplace such a prevalent issue in vulnerable populations. And to conclude, we learned that measuring environmental exposures is critical for public health, and that exposures can be unequally distributed in disadvantaged communities, and that exposures can get into the body and affect health, contributing to health disparities, and that toxicants and other social factors commonly co-occur. So there's really a need to think broadly about structural inequalities that make certain toxicants so pervasive so that we can really solve these very complex life, real challenges that we find in public health. And so I would like to acknowledge the grant that funded this conference and the JPB Environmental Health Fellowship Program. And please email us with any comments or questions at the conference, or my email, ceballos@bu.edu. Thanks, everyone. It's a pleasure.